Hello, my name is Zentgraf and I'm presenting you our software xengsort, which is joint work with Sven Rahman. We are dealing with patient-derived xenograft data. In our case, we want to sequence human tumors which are grafted into mice. Since we only want to analyze the tumor reads, we need to decide for each read if it is a host read from the mouse or a graft read from the tumor. There are two ways to solve this problem. One is the traditional way, the alignment base, where you align each read to a reference genome of the host and a reference genome of the graft, and then classify it depending on the resulting alignments and quality matrices. The other way is to use alignment-free tools like Xenome or now xengsort, which work directly on the raw reads, and use an index of the references to classify these reads. We use a carefully engineered alignment-free approach and use a three-way bucketed cuckoo hash table as an index to achieve a high accuracy for our classification and a fast running time. So our problem is that we have a lot of reads from mouse or tumor and we want to assign them to one of our 5 categories: host, graft, both, ambiguous, or neither. The basic idea is that we build an index of the reference genome using our three-way bucketed cuckoo hash table. To do this, we divide the reference genomes into k-mers, store each k-mer as a key and the corresponding species as a value. If a k-mer occurs in both references, we store both species. After that, we calculate the Hamming distance between all stored k-mers and mark these k-mers that are in different species but have a Hamming distance of 1 as weak. After we build our index, we want to classify each read, and to do this, we divide it also into k-mers. And for each k-mer we query the corresponding species in the index. After we did this, we assign a category based on the species values, and to do this we use specific rules. These rules are shown as a decision tree on the top right. We start with an easy decision. If we have no graft or weak graft, we can't assign it to the graft category, and if we have no host or weak host, it can't be host. The problem is, most of the time, we have a mix of these values. We have some weak graft and some host k-mers, and we have to decide, okay, it's host or it's graft, and to do this, we empirically derived thresholds and formalized them in the decision tree you see here. Let's have a short look at the experiments. We compare 3 different tools: xengsort, our tool, which is k-mer based; xenofilter, which is alignment based and uses BWA-MEM to align the reads to the reference genomes; and Xenome, which is also k-mer based. We assign each tool 8 threads per run. In the following evaluation, we will see that xenofilter only output reads that it classifies as graft. So we only have a bar for xenofilter in the graft part. Let's start with the most interesting dataset, the PDX RNA. Here you can see 2 bars for xengsort. The blue one uses the normal classification rules, and the purple one uses a quick mode, which only checks a few k-mers at the beginning and the end of each read. As you can see, all tools classify between 70 and 75% of the read as graft, xengsort the most, xenofilter the least. Xenome has some more reads classified as ambiguous in comparison to the other tools. The second dataset is the chicken genome. Here we expect that most of the reads are classified as neither, and as we can see, nearly 98% are classified as neither, a little bit as host, graft, both, and ambiguous. In comparison, Xenome has a lot more reads classified as host, graft, both, and ambiguous. Xenofilter has nearly no reads classified as graft, so the bar is really small. When we started analyzing the leukemia RNA, we expected that most of the reads are graft, but as you can see, a lot of reads are classified as neither by xengsort and Xenome. We investigated on these reads using BLAST and blood, and we think that there's probably a contamination in these dataset. Nevertheless, there are still a lot of reads classified as grafts. The last dataset that we analyzed are the mouse exomes, which are captured with a human exome capture kit, and as you can see, xengsort nearly classifies all reads as host, xenom a little bit less, and xenofilter only classifies a very small amount of reads as graft. At the end, let's have a short look at the runtime. As you can see, the alignment step using BWA takes over 284,000 CPU minutes, and xenofilter needs additionally 16,000 CPU minutes to analyze the alignment. Xenom is a lot faster. It only needs 60,000 CPU minutes, and xengsort is even faster than xenofilter without the alignment step and only needs 13,555 minutes. In the lower part, we compare different options for xengsort. The normal one is a hash table filled up to 88%, and we compare to a hash table with a fill rate of 99%, which shows us that the fill rate of 88% is faster, and we optimize both, and we can see that the optimization is always faster than the unoptimized version of the hash table, but even if we optimize the full hash table with 99%, we can't achieve the runtime of the optimized version of 88% fill rate. The last bar shows us the quick mode, and you can see that's a big runtime improvement because we only need 5,713 CPU minutes.